I'm ready to get started. We keep going onward and onward, right? That's the way it should be, though. Can't have a rest. Spring break is the first rest that we'll have, if you can call that a rest. Okay, we're jumping back around in this chapter 3 with Fourier series details. We kind of looked ahead. I jumped way ahead and looked at frequency modulation, or chirps, which you got to experience on Friday. And now we're going to go back and look at some details of Fourier series, which is pretty mathematical, but then it'll boil down to some fairly simple calculations, but some will be tedious. Actually, this topic area is probably the most challenging math that we'll run into the entire semester right here. But we're not going to force you, I say we, meaning the labs and me, are not going to force you to do an extensive amount of detail in this, because it is an area that I know can just push you over the limit pretty easily. But when you get on further in signals and circuits in 3205, you'll come back and see some of this again. If you take communications and digital signal processing, those are two areas that I teach in, you'll see even more of this. So this is a topic area that has an analogy to painting a house or painting think of a piece of wood. I mean, I'm not going to tell you your brain is a piece of wood, but it's kind of, there's an analogy in there, and the analogy is this: multiple coats, so it seeps in, and finally you've got a real, dense coverage of the material, and it's soaked in, and you're getting it. So this will be pass number 1 as we go through this right now. One of the homework problems last week pertained to finding the Fourier coefficients. And it was the A sub k's, and I looked ahead at one of the examples that lies beyond this in the notes, and we looked at how, if we have a special case of a cosine, a number of cosines that constitute a signal, we can get by inspection or kind of doing some manipulation using Euler's inverse identities. You can discover what the A sub k's are. And one of the neat things about Fourier analysis is once you find them, you've got them. No one can take them away from you, so to speak. I mean, they're unique. So if you can find them by any means and they fit this model, that's all there is to it. You don't have to go through elaborate integration techniques if you can find it by some other means. And that last homework problem involved finding it by another means, but now we're going to look at finding it formally, which is via an integration formula. So that's the so-called analysis formula. The synthesis formula is the fun part, where you've already got the coefficients found, and you're just going to synthesize a waveform using this equation 322. The analysis side, as we briefly were looking at last week, involves having to do this integral. Does anybody have any reaction? Does that look on paper, and it's on paper right now, does that look moderate, challenging? I mean, what looks ugly about it? Does anybody want to? Well, it's going to depend on what x of t is, but does anybody want to cite what looks the ugliest about it right now, just sitting there on the page? The complex exponential. That's what I would rank as high. Those of you in the class that are still taking calculus, everyone has done something with exponential functions by this time. That probably is Calc 2 maybe, or the end of Calc 1. I don't know. Where you have to integrate e to the x, or e to the ax. That by itself is not too bad, but as was pointed out, suppose there's a t out in front of here, or there's a t squared or a t cubed, and then you have to get into integration by parts and some other fancier stuff that just doesn't stay in your brain. Actually, I shouldn't put t in there. I should have put x in there. Stuff that doesn't stay in your brain for very long. It should be in your brain somewhat solidly because you've just had calculus recently, but I have to go back and review it if I'm going to do integration by parts. It makes me think back to a roommate that I had in college who had a little jingle that went along with memorizing integration by parts. And I don't remember it exactly, and it probably wasn't a good thing to say in public or something like that. I mean, I lived in the dorms, and like I said, he came up with this jingle, and that was his way of remembering it. Is that yours? You've heard it?
I got it from the math teacher.
Okay. I won't even try to remember it because I'm sure it was something not to be said in public. This guy was a chemistry major. I don't know if that means anything. None of you are chemistry majors, or is anybody in here ever a chemistry major? So what do we have to do to get there? Well, we're going to look at the derivation of this formula, how we get to it. Our primary focus in this class will be responsible for one special coefficient, and that's going to be when k is equal to 0. And that just gets us a single coefficient, the DC component. And this is kind of rudimentary, but it gives you a flavor of what the calculation is like, and it also extracts an important piece of information about a waveform and things that will actually have an influence on your studying of circuits and systems and even into electronics next year when your juniors taking electronics 1 and 2. T naught is the period, so whenever we consider a Fourier series idea, we have to have a periodic waveform. So from the very get-go, we have to consider a waveform that's periodic. That's where the Fourier series representation comes from. So going back over to here, this formula relies on the fact that basically this waveform is periodic with period t0. You're probably thinking, what if it's not periodic? What if it's aperiodic, which means it just happens once and then it goes away? Then there's another Fourier result called the Fourier transform. So we have another type of representation for aperiodic signals. But this is for the periodic types. So how do we derive this? How do we get that synthesis formula? The analysis formula, the one that's boxed in red. How do we get that to correspond to the Fourier series itself, where there's a couple of steps involved? So there's some background that some of this is going to be familiar to you and some of it's going to seem totally new and different. First off, we need, in order to get the proof of this analysis equation, we need to just consider this integral, this first integral. We need to consider that I'm saying it's equal to 0. And how can we verify that? Well, the first thing we could do is pure brute force. And that's number 1. So pure brute force is just to use what you know about the antiderivative of e to the x. So if you want to take and integrate e to the x, you have to take and divide by the exponent, right? So if we were integrating e to the x, we have to take e to the x over x. Well, actually not e to the x over x, we have to take everything less the independent variable. So let me not try to write that so simply. I'll just rely on your understanding of calculus. If you have e to the something times t, so we have e to the, I'll just say e to the at, that integrates to e to the at over a if we're integrating with respect to t. So that's exactly what I've done here. Taken e to the j 2 pi over t naught times k times t, and then divided by everything but the t that was sitting up there in the numerator. And admittedly, it looks messy, but it's not something you're not familiar with, right? Because e to the at is something you can integrate. True or false? I mean, it's easy. The messiness, though, is, something you got to learn to live with. Just dive in and hold on, basically, to all the details. So now I put in the lower and the upper limits, plug in. We know that e to the j0 is 1. So we get, from the lower limit, we get this 1 over here, and from the upper limit, we just have the t naught plugged in place of the t. And that is equal to 0. The reason why is that no matter what the value of k is, for k equaling 1, 2, any integer except 0 in this case, because we're not going to deal with that instantly, although I'll comment on it here in a second. As long as we're dealing with an integer value, e to the k is equaling a positive or negative integer, we're going to have, in that complex exponential, we're going to have those guys cancel, and then we just have something in the exponent e to the j 2 pi k, which is equal to 1 no matter what the value of k is, right? Does everybody see that from Euler's identity? Because that's cosine of 2 pi k plus j sine of 2 pi k. Or, it's a mod 2 pi function, so it's just 1. What about k is equaling 0? What would we have to do to evaluate that case? We don't really need it at this moment, but we're going to need it in a second. What happens if k is equal to 0? From this version number 1 at least. It looks like if we go from this guy over here, it looks like we'd have to use L'Hopital's rule, right? Because we have an indeterminate form. As k approaches 0, we get 0 over 0. And that will work. Another way of getting at it, though, would just be to go back over to here and just plug in k is equal to 0 and consider that case as a special case of the integral. And if we were doing that, we'd just have e to the j0, which would be 1 integrated from 0 to capital T naught, which would evaluate to T naught, right? We just integrate a constant over T naught seconds. Number 2 technique, this one might be a little bit more reasonable, and I'm just showing these two methods because sometimes your brain gets overwhelmed by the complex exponential and you don't want to do it that way. You'd want to break it into smaller pieces. So you can always use Euler's identity first. So then you're going to get two terms, the cosine term and j times the sine term. But a fundamental property of cosines and sines is when you integrate them over an integer number of periods, what happens? Whenever you integrate a trig function over an integer number of cycles, what do you get? I'm assuming that you've done this somewhere else. If the cosine function, whenever you do this over an integer number of cycles, you're talking about on that interval right there, which I didn't draw super beautiful. You got this area is positive, which is the same equal in magnitude to the area under the curve, or the negative side, so the area is equal to 0, right? So therefore, both of these terms, the sine and the cosine term, integrated over any integer number of cycles, which holds for any value of k not equal to 0, will always integrate out to 0. So that's maybe an easier way of seeing it than the first technique. Anybody comment? Or if this is really obvious, I'll just keep moving, but stop me if it's not. Okay, so that's the first observation we needed to make. Integrating a complex sinusoid over an integer number of periods is equal to 0. Next thing is, the periodicity of complex sinusoids. I think we've talked about real sine and cosine being periodic, but let's just check into a complex sinusoid. Is it periodic, and is its period t naught if it's written as it's written here? So on the next page here, I just simply take the periodic function v of t and replace the time argument by t plus t naught. So I advance it by one period, and I just want to see if it equals the original v sub k of t. So you put t plus t naught up into the argument, and then multiply it out into what was the original first term without the time shift, and then the t naught term is this guy right here, but that means that that is canceling. So that says that this term just reduces down to e to the j 2 pi k, which again is going to be equal to 1. I had an error in the notes that I discovered just before class, and I changed it from 0 to 1 because it was just a typo that I had in there. So if you're looking at a copy, that is supposed to be 1, because e to the j 2 pi k for any value of k is always going to be cosine of 2 pi k, which is 1, and sine of 2 pi k will be 0. So we established that complex sinusoid is periodic with period t naught as written. Now the final property that's needed to get this analysis equation proven is what's called the orthogonality property. I think everyone in here will probably be taking linear algebra at some time. Have any of you seen it on your schedule? Okay. What do you know about vectors right now, though? If you have two vectors and you take the dot product between them, now I'm saying you don't have to have linear algebra to know about dot products, because I think you study that in physics. You have the I, j, and k unit vectors in physics. So I dotted with I is 1. I dotted with j is what? 0. So those three unit vectors, which all I've got to do is stare at the corner of the room. I remember this from when I took statics and dynamics, mechanical engineering courses. They'd always say, look up in the corner, there's your I, j, and k unit vectors sitting there in the corner. You ever do that to you in physics? Make you think like that? But that's kind of a visual of them, as long as the walls are true, which that's the contractor that built the place. So they're mutually orthogonal, is what I'm saying. So an abstraction to that is to say that functions can be orthogonal, mutually orthogonal. And that's what this property is all about. It's saying when considering an integration over a particular interval, and this is called abstract vector spaces when you finally take linear algebra, we can talk about an inner product being defined, or a dot product being defined as the product of one function times another function and then integrated. If that is equal to 0, then we say those functions are orthogonal on that time interval. So that's what this property sets out to establish, that if we take vk of t times v sub l conjugate and integrate it over one period, we get 0 if k does not equal l, and we get t naught if k equals l. So under this condition, this is like dotting the I unit vector with the I unit vector. We get its length squared from from analytic geometry. So you can say that t naught is like the length squared of these functions in an abstract vector space. Plug that into your deep memory for later when you take linear algebra. You might actually say, hey, I remember that. Okay, now what is v conjugate of L? It's just taking the conjugate of this entire complex exponential, but we know what the conjugate operator does. It goes looking for j, and it wants to change the sign on j, because that's what the conjugate operator does. It makes the imaginary part have the opposite sign. So in this case, it's making that become a minus j. So now we're going to go ahead and jump in and plug these two functions into the integrand and integrate. So plug those together because this second term has the minus sign, and we have a k in here and an l in here. We're left with e to the j 2 pi over t naught times the quantity k minus l. So for the special case where k is equal to l, then that exponent goes away, right? Because we have this guy going to 0 when k is equal to l. So we integrate e to the j 0 on the interval 0 to t naught, and we end up with just the constant t naught. So that proves part of the property, and then the other part is if k does not equal l, we can just say that it's some integer, k minus l is some integer m, and we're just integrating a complex sinusoid over an integer number of cycles, and as we were looking at moments ago, that's always going to be 0. So that's the orthogonality property. So now here's the power part, powerful statement. And I guess this is what Fourier's thesis was all about, making these observations. Now that we have the background, now we start with this Fourier synthesis formula, which says how we can represent x of t in terms of coefficients and complex sinusoids at various indices k from minus to plus infinity. Now what we want to do is find the a sub k's using this analysis formula. So this is going to seem kind of like an arbitrary thing, but what this proof entails is just saying let's multiply both sides of that equality by something, and then let's integrate both sides by that same over the same interval. In other words, treat both sides identically. It's like we have this on one side, this on the other. Let's multiply this side by the same thing we multiplied by the other side, maintaining equality. Then let's integrate this side from 0 to t naught, and then let's do the same on the other side. So we're doing parallel operations, one on each side. And so we do that. We do the multiplication here and here, multiplying by e to the minus j 2 pi t naught lt, and then integrate both sides. And then focus our attention on what's happening on the right-hand side. And another important step of what's going on the right-hand side is this, something that requires some engineering math hand-waving, I'll call it, and that is, in pure mathematics, if you want to interchange that sum with the integral, we have to know about a certain type of convergence. Can you remember in calculus talking about convergence of things? What did you learn about convergence? Was it a delicate matter or was it always an easy matter? Okay, you're right. It is very delicate, and mathematicians don't take it lightly. Engineers take things a little bit more laid back because we want to use math for its functional, operational sense. We want to get problem solved. We want to get some practical insight into something. So we know in the end that in order to make this proof work, we have to have certain convergence properties hold for us to be able to swap the sum on the outside and the integral on the inside. And that's beyond the scope of this class. So you're just going to have to take it on faith that we can, under certain circumstances, and a lot of books would say for signals of engineering interest. Does that sound like a good catch-all? For signals of engineering interest, we can do this. And even for the signal models we're going to look at, it does tend to break down, but we still have a certain type of convergence holding, and it's called mean square convergence, which we'll look at a little bit later. So we interchange the order of sum and integral. So now we have the integral on the inside, and this integral on the inside is looking like the orthogonality condition we were just studying moments ago. It looks like we have an e to the j times an e to the minus j. One is in terms of k and the other is in terms of L. So we just learned that that particular integral is equal to 0 for what? K equals L and is equal to t naught otherwise, namely for k is equal to L. So when we have a condition like that holding, that does something very nice and slick for us. It takes this sum, which runs from minus to plus infinity, and says L is staying fixed on the right-hand side there, but k is varying. But as k sweeps on by from minus infinity up to plus infinity, it hooks on to one value, namely when k is equal to L, where that integral will produce a non-zero value. And that's the only value then that survives out of that doubly infinite sum. Can everybody see that? It's a little bit abstract, but when you interchange the order of sum and integration, we end up with this neat result that that integral on the inside is 0 everywhere except k is equaling L. So when that happens, we hit, so to speak, we hit something where we get a non-zero value. So we're going to get, out of this integral, we get t naught out of this whole thing when k is equal to L, 0 otherwise. And so the value that hits out of that sum is just going to be, if I carry this down, it's just going to be a sub L times t naught, which actually I wrote out down here. So the only value that hits is when k is equal to L. All the rest of the values go away because of that orthogonality. And then we're left with, if we just take this piece right here, the t naught, and move it onto this side as 1 over t naught, take that out, and then flip-flop the equation, so the a sub L is on the left and the integral is on the right, then we've got, the analysis formula proven, except it's in terms of L rather than k, but it's the same idea. It's an equation that tells us how to get the Fourier coefficients in terms of this integral. Now, a little bit more thought can also give some insight as to then what the Fourier analysis is doing. And I can look back behind me at the corner and the ijk unit vector sitting up there, and I can just imagine that we have a three-dimensional space composed of three different complex sinusoids. So really what we're doing here is we're expanding these e to the j 2 pi t naught over t naught kt is like the ij and k unit vectors. And what we're doing by this is we're saying we can represent an arbitrary periodic signal as an expansion in terms of an arbitrary set of orthogonal functions, like the ij and k unit vectors are orthogonal vectors. So we get the a sub k's then are, in the ij and k unit vector sense, what do you do in analytic geometry or in vector analysis? What's that all about? You have a vector out in a three-dimensional space, and in order to represent it in terms of the ij and k unit vectors, what do you do to make that, to construct all that?
Is it part of angles?
It's part of angles, but what's a more general term that you might remember? It starts with a P.
Feet.
Projection. Remember the idea of having something out in space, pretend my arm is that space, and now I project the component of this on the x-axis, the y-axis, and then up on the z-axis. So what the Fourier analysis is doing is it's projecting the a sub k's represent the projection in terms of a complex magnitude of our signal onto these various complex sinusoids. So it's the strength then of x of k as it projects onto the various harmonics, the e to the j 2 pi over t naught times kt functions. And So we get projections into first, second, third, fourth, fifth harmonics and so on. How strong a representation does the signal have in these various harmonics? And we were studying just prior to this the line spectra. So we're actually can see from, say, the magnitude of those Fourier coefficients, how strong a fundamental do we have, how strong a second, and so on. Does that sound kind of cool, or does it sound too abstract? It's actually very valuable, but you got to get your head wrapped around the idea. I say it's valuable because if we have an arbitrary periodic signal, we do have an interest in what its harmonic content is. We might use that to design a filter to eliminate some of the harmonics that we think could be harmful to our system. We might try to modify certain harmonics content to change the nature of the signal. I mean, in music, changing the content of the harmonics changes what's called the timbre, which is the sound an instrument or a singer's voice would have. Could be better, could be worse. But computers are certainly used a lot. Computer modeling and real-time processing is used now more than ever so that you can modify the timbre of an instrument. You can synthesize an instrument, so you can have a synthesizer represent the sound, and that's the subject of Friday's lab, is synthesizing sounds. But then there's even more exotic things we move down to that the Fourier analysis doesn't exactly do, but something called pitch shifting. Has anybody ever heard of that before? That's not Fourier analysis per se, but it's another avenue that you can go down with real-time signal processing. Pitch shifting says that you can take and change the pitch of something without changing the duration. I mean, in MATLAB, you ought to try sometime. Everybody worked with sound last week, right? The sound or sound SC function. The second argument you put inside of there was the sampling rate. And I'll probably demo this. Maybe I'll even do it here in a few moments. I'll think about it. If you make it the sampling rate that you use to play the sound back faster, it's going to play back faster and it's going to raise the pitch. If you make the sampling rate slower, a lower frequency value, it's going to play back at a slower speed, and that's going to stretch the sound out so the pitch now lowers. In both of those scenarios, though, you're getting a pitch shift, but you're also making information either play for a shorter time or a longer time. If you were interested in making it play for the same time, then that's where the idea of pitch shifting comes in. It plays for the same duration, but you want to shift the pitch up or down slightly. And think of American Idol, that TV show that some of you probably watch. My wife likes to watch it, so it's on, and I sometimes look at it. If a person doesn't have perfect pitch, what could pitch shifting do for them? In theory, it could make somebody that doesn't sing very well sound really good. And I've heard stories that actually that gets used a lot, or at least if you want to record over yourself and sing harmony or something, and your harmony's not quite beautiful sounding, you can just pitch shift it and kind of make it sound better in the recording studio. Do you believe that's done, or do you think that's just fantasy? Pardon me?
Auto-tune.
Yeah.
Like, yeah.
TV's been in on it.
They did it on the Super Bowl.
Okay.
Doesn't
But
have
you
to.
can tell usually
Yeah.
that it's being done. It's not like it's.
It's really like.
So you think it sounds artificial,
It
or
sounds
can?
robotic.
Yeah, you're not
Okay.
going to get a really good, like, Celine Dion style performance out of it without noticing.
Not a natural.
But I think,
Not the natural part is what I was aiming at.
but actually, for some of you, if you went into this sort of thing, you'd probably find that the music people are pushing the engineers harder and harder, saying, make the algorithms, make the processing better and better, so no one will know that this has been doctored up to sound perfect.
Well, that's why people on album or artists on albums, they sound good, but then you hear them in person and then they're at their live concerts and.
Okay. So maybe there's a moral to that story. Some people are gifted and some people are not. And at one time, we just heard the people that were the most gifted to sing, and that was that. And then everybody else that had an aspiration to sing eventually decided they'd do something else. I don't know. That's not an engineering topic, though. Take that up in some other class, in LAS probably. But engineers enable things like that, though, because we're called upon to innovate on things like that. Okay, an example that we looked at last week that doesn't require the Fourier integral, getting the coefficients from the analysis equation, was just this guy. And I'm not going to go back and visit that one right now, but I'm just passing through it. What we do want to home in on right now is an example. So we're going to look at a square wave signal. Once we get the Fourier coefficients, then we'll come back around and we're going to play with this. We're going to say, okay, now that we have a Fourier representation, Fourier coefficients representation for some periodic signal, let's see what happens if we approximate it. So we're going to do an approximation using, say, the first n harmonics. And I'll probably let you take a stab at this in the next homework assignment sheet, not the one that I've got up right now. Just try to mimic some of the stuff I put in the notes and put a plot together in MATLAB of how you can synthesize from harmonics a periodic waveform. So the first example is the square wave, and this is a classical waveform, and it's a waveform you're familiar with from logic circuits because it's a clock signal, right? An ideal clock waveform would be something that's on for half the time and off for half the time. So we'd call this a 50% duty cycle square wave. And duty cycle, in the terms of power systems or anything you might visualize out there in a shop environment or something, is exactly that. You're making the waveform be high for half the time and be low for half the time. You're drawing the light bulbs on for half the time, it's off for half the time. So the duty cycle is 50%. So how do we do the Fourier analysis of this waveform? Well, first off, the fact that I've got one period there darkened in was on purpose. It's saying that for the Fourier analysis, we just need to consider what's going on one period. So we're going to be integrating over that fundamental period, 0 to t naught. But it turns out, from the math, I could pick, my period could be picked over here. I could pick the period like that. All that matters in the Fourier analysis equation is that I integrate over one period somewhere. For this first example, we're doing it from 0 to t naught. So I plug into that integral, and the first thing I do is I do a piecewise integration because I recognize that the function is only 1 on the interval 0 to t naught over 2. And then over here, I nominally had an integral that went from t naught over 2 to t naught, but its integrand was 0 times e to the minus j, 2 pi over t naught times kt. So you want to dispense with that immediately, right? Do you even want to write up an integral that's 0? I mean, that's why I didn't put it on the page, because I knew that was 0. So now we integrate that, and it integrates from 0 to t naught over 2, and I set up the antiderivative, set up the lower and upper limits, and then plug in, and it boils down to this right here. Is that beautiful looking, or is that kind of messy looking? I know you haven't been dealing with e to the j's prior to this semester, so, and then you have a j in the denominator and a k down there. My contention is it's kind of ugly looking. It's not particularly beautiful at this point. What we can do, though, is we can do a little bit of work on it. We can notice that e to the j pi is equal to minus 1. So what happens if we have e to the minus j pi to the kth power? Because that's the same as this thing right here. My j pi is a little bit sloppy looking. Right? So if e to the minus j pi is minus 1, then e to the minus j pi to the kth power is minus 1 to the k. So I can then make that substitution in that equation as 1 minus the quantity minus 1 to the k. I still haven't gotten things really beautiful looking, but there's an interesting result that's going on there in that numerator. Combine the first term in the numerator with the second term, and we've got this toggling action. We've got the two terms are combining and then they're canceling. So we're getting reinforcement and then destruction or annihilation going on. So when you see something like that happening, we can then simplify further and say that that AK term is actually going to be equal to 0 when K is what? An even value, because minus 1 to an even power is always going to give us 1. When K is odd, we're going to have the constructive interference between those two terms. And then along the way, we can also notice that when K is equal to 0, of which this term does not handle, K is equal to 0 without using L'Hopital's rule. But if we go back and just take K is equal to 0 as a special case, then we get just this integral right here, which is the average value, or the A0 term, and that's just going to be equal to 1/2. I can get that by inspection, but if you want to plug it into the integral, you just have to integrate 1 on the interval 0 to t0 over 2, and that gets you t0 over 2, and then divide by t0, and you get 1/2. Like I said, the DC value, or the average value, which is what A0 is one of the terms that I definitely expect you to be able to calculate in this class. And if we go back up here to this picture and just drill down on one period, does it make sense that A0 is equal to 1/2? Because it's representing the so-called average value. So half the time the waveform was sitting at 1, half the time the waveform was sitting at 0, so on average it sits at 1/2. If you're in the lab using a DC voltmeter, an instrument that measures the average value of a waveform, or the steady value coming out of a supply or a battery, it would measure 1/2, because it would average over all time and say half the time it's high, half the time it's 0, it averages to 1/2. That's why I have the dashed line drawn through there. That's pretty easy calculation. And just to give you a quick look at something on this worksheet I handed out, I give you that kind of a waveform. We're going to look at this a little bit later, find the average value of that waveform. You can do that, right? Just find the area above and the area below over one period. It'll be pretty straightforward calculation. Okay, so now we have all the details that we need. We just need to organize it. So we know that at K is equal to 0, we have 1/2. So that's the A0 coefficient. And then we just take and simplify this term for K is odd and K is even. So when K is odd, the AKs, except for K is equal to 0, are annihilated to 0. And when K is odd, we get a 2 on the top side, and we have a 2 in the bottom, so we have 1 over j pi k. Still a little bit messy looking, but it's as clean as you can get for a Fourier series representation for a square wave. So this tells us that a 50% duty cycle square wave has, as defined here, has an average value of 1/2, doesn't require or has no representation at the even harmonics, and then at the odd harmonics, the coefficient values are 1 over j pi k. So the important thing is that the AKs, when they do exist, which is for K odd, The fall-off rate of the Fourier coefficients is 1 over k. So they fall off inversely proportional to the harmonic number. So the first is the strongest, the third is at 1/3 relative to the first, the fifth is at 1/5, and so on. So they're dying out in the waveform. So if I use the line spectra function that was introduced earlier in the notes and just set up a little MATLAB routine to generate coefficients, I can then get the line spectrum, magnitude, and phase for the square wave that was just talked about. We see spectral lines at DC. That's because of the average value being 1/2. And then we have the first harmonic. Now these guys are the k is equal to plus and minus 1. Then the third harmonic, plus and minus 3. And then fifth, and so on. And we see that the amplitude or the strength of the harmonics is falling off as we go up higher in frequency. How did I load this stuff into the function up above here? I kind of played some games with it to use the function. I had to load in the x. I had to convert the a sub k's back to the original x sub k representation by multiplying by 2. And then I set up an index in MATLAB k that runs from 0 to n up to the 15th harmonic, but I had it stride or step in steps of 2, so it goes 1, 3, 5, 7, and so on. So then the x sub k's were meant to correspond to that index k. Notice this guy in here, just as a review, why is that in there? And I want to do a pointwise division, and k is a vector, so I needed to make sure I did a point-by-point divide by the elements of k. Some of you were getting zapped by something like that in the lab on Friday. Not dead or anything, you just have to fix your code, but it happens to me too. I get in a hurry and I type, and then I get that dinging sound from MATLAB and I have to go fix it. And then the other thing I did to get the DC value in, I just augmented the k vector by putting in 0 frequency and then forcing in the 1/2 for the DC value. And then loaded it in, and the plot gets generated. If I want to synthesize the square wave, in other words, go back and synthesize using up to the 15th harmonic, I took the original synthesis sine function and modified it. And you can see that I didn't change the name of it in my function file entirely, and called it Fourier series synthesis, so that I could just load in an equation for the coefficients, the harmonic values, the sampling rate, duration, and t start. And again loaded that up with the Fourier coefficients from the analysis we just did. So again, the coefficients, I just stepped them from minus to plus 15 in steps of 2, and that gets me all the odd harmonics. And then I stuffed into that the DC value, so entered in A0 manually. Plug it into this Fourier series synthesis function, and then, because the mathematics of MATLAB is not perfect, the x values here are going to come out with small imaginary parts, even though I know I'm synthesizing a purely real waveform. And this, I guess, brings up a good question. I'm going to represent a real waveform with complex sinusoids, but because of the fact that I started off with a real waveform, the Fourier synthesis formula is going to return to me a real waveform. It's just that the imperfect math of MATLAB means that there might be tiny, tiny little imaginary parts. So it's fair to just say, let's just suppress those in my plot by taking the real part, because I know a priori that the synthesis of a periodic waveform using a Fourier series representation is purely real. And in this case, it all has to do with the fact that I've got an AK times an e to the j 2 pi over t naught kt. And then I've also got a matching e to the minus k e to the j 2 pi over t naught, or e to the minus j 2 pi over t naught kt. And I know a property of the Fourier series is that AK conjugate is equal to e to the is equal a to the minus k. So I know that from Euler's identity that those two complex exponentials with the a to the k and a to the minus k will go back together to form a real cosine. And there's no imaginary part there. So I synthesize it using just the first 15 harmonics, actually up through the 15th harmonic, not 15 harmonics in total. It's just first, third, fifth, 7th, 9th, 11th, and so on. And that's as close as I can get to getting a square wave. It has what are called ears, at least that's what people call it. It's like it has ringing or ears on the edge of the square. It turns out that the Fourier series representation of a waveform that has discontinuities in it, you cannot get absolute convergence everywhere. You can only get it pointwise convergence. So the ideal square wave jumps back and forth. And it has problems trying to represent the discontinuity, and as a result of trying to handle that discontinuity, the jump that occurs from here up to here, it then kind of gets into a turmoil and it ends up ringing. So it overshoots, undershoots, and then tries to damp out in between. So it's damping down to a smaller value in here. But then the next discontinuity comes along and then it gets all whacked out again. It starts ringing again. And this is due to that discontinuity. Now, in a real electrical engineering waveform, can we build a generator that has that discontinuity? Does physics allow us to take a voltage and instantaneously move it up to a higher voltage? What do you think, with what you know right now? It has to really be continuous. There's no such thing as a discontinuity like that in a real waveform, because we have distributed elements in producing that waveform. We have capacitors and inductors and other storage elements that end up making the waveform go through some continuous path. We still can have ringing, though, when you try to represent a square wave without all of its harmonics, but it's going to be to a lesser extent than this, because instead of having the perfect jump, we end up having something that actually has a finite rise and fall time. So there's actually a transition in there. If it's a slow clock, and we'd have to zoom way in on it to see the edge transition, but there's actually a small slope there, or I mean a slope that's finite rather than being infinite. Now, as we change the number of harmonics, the number of oscillations or rings goes up and down. So for 3 terms, first and third harmonics, we get this first waveform, first, third, fifth, and seventh, and then up through the 15th harmonic. But the ringing always stays fixed, so that the amount of overshoot, as this little note here said, is always at 9%. It doesn't change. It's just the rate at which you ring gets finer and finer as you go up in harmonic number. Okay, before we go further, I'm going to just give you an example where this Fourier modeling is useful in building a radio frequency circuit. Let me see if I can grab this. There's wires on the back that might poke you, but I'm going to try to flip it so that you can hold out two hands, and that hopefully won't stab you anywhere. There you go. That circuit I'm passing around, which I'll be using in a demo on Friday, is this frequency tripler circuit. In digital logic, you've learned about you've learned about digital dividers, right? You can have a clock signal at, say, 10 megahertz, and if you divide it by 10, what do you get? A clock at 1 megahertz, right? Now, what about going the other way? How can you go up in frequency? You can think. A phase lock loop synthesizer could do that, but a way of doing that with passive electronics would be this idea of a frequency tripler. This would to be the 3x multiply the frequency is what the tripler does. And in radio frequency circuits, a lot of times you generate from a standard clock a higher frequency signal using some nonlinear processing block, such as this tripler. It's connected with the idea of frequency synthesizers, though, too, where you'd use something called a phase lock loop, which gives you the digital tuning capability that most radios have today. But this way is still practical and has value, and it also is a good example of Fourier analysis. So we start off with a cosine wave that's at frequency f0, and then we send it through this limiting circuit. The limiting circuit is like a comparator that you might have seen talked about in logic circuits. I'm not sure were comparators talked about in logic circuits. Or no? Probably not, they are or not.
Sounds familiar.
Not so far in mind, but
Okay. Probably talked about in electronics for sure. The comparator is just a special logic gate that can take an analog waveform, and if it's positive, it rails it at 1, let's say, and if it's negative, it rails it at -1. Or more likely, it might just rail it at 0 and 1, but I'm showing it as if it can rail or clamp the signal to either -1 or +1. The idea is, though, we can take the sine wave and we can convert it to a square wave by going through a nonlinear processing element. And on the circuit I'm passing around, there's two black devices that are back-to-back, soldered back-to-back, and those are diodes. They're actually a high-frequency diode called a Schottky barrier diode that are put back-to-back. So I'm putting a little diode electronic circuit across there. That looks like this. And those diodes conduct in one direction and they don't conduct in the other, and when they conduct, they clamp the signal to a certain voltage drop. So those diodes can convert the square wave or the sine wave to a square wave, and I'll show that in the demo on Friday. So now that we have the square wave, it's got the same period or same fundamental frequency as the sine wave. We know that the square wave is going to have only odd harmonics. So we'll have f0, 3f0, 5f0, 7, and so on represented once we go through that circuit. If we're building the frequency tripler, we're interested in capturing the harmonic where we have k is equal to plus and minus 3, because that will give us a cosine at 3 pi times f0, the tripled frequency. Now the trick is we need to follow up that clipping circuit or limiting circuit with something we've only intuitively talked about, and that is filters. In particular, we need to follow it up with what's called a bandpass filter. What the bandpass filter is going to do with regards to the frequency axis down here, the signal comes in as just two spectral lines, plus and minus f0. It comes out of the tripler or the limiting circuit with spectral lines at f0, plus and minus 3f0, plus and minus 5, and so on. For the tripler, we just want to retain the plus and minus 3f0 spectral lines, because that corresponds to the cosine of 3f0. So the bandpass filter comes along, and it has the ability to sift the signal such that we only retain the third harmonic. So the rest of the elements that are on the back of that circuit I'm passing around constitute a bandpass filter built with inductors and capacitors. So you see little brown shiny parts that are capacitors, and then tubular devices that have stripes on them or bands on them are not resistors, but they're actually inductors. So they're coils of wire around a ferrite core that's encapsulated in plastic. Most of you are familiar with, there's a color code for resistors. There's a color code for inductors too. And inductors you learn about in circuits and systems, 2205, 3205, but I think you've seen inductor circuits probably in physics too, where you studied circuits, right? Some people consider inductors to be nasty. They say nasty inductors, just because you got to wind wire around something to form an inductor, and it's just a little bit not so easy to deal with. And then there's other properties of them that aren't always fun. They're a magnetic circuit element, or magnetic field-based circuit element. So I'll demo that on the spectrum analyzer, and we'll also look at the waveform on the scope. So understanding the nature of the Fourier series representation is critical to being able to make this frequency tripler work. If the square wave didn't have the third harmonic, what would we have to do? I mean, if limiting the circuit or clipping the circuit, going from sine to square, didn't end up generating harmonic components at the third harmonic, this technique would not work. Furthermore, if we couldn't rely on the fact that the second harmonic, which is, let's see, second harmonic should be down in here, right? That's 2F0. And then the fourth harmonic, 4F0, are squeezed in there. If those were not zero, in other words, there was a representation at the second and fourth harmonic, then the design of the bandpass filter would be more critical, because we'd have to make sure that we did not pass any of those signals through. So we're also relying on the fact that the design of the filter is relaxed somewhat because of the fact that there's no need to worry about eliminating with our filter the second and fourth harmonics. Does that make sense? Now, what do you think a real limiting circuit's going to do, though? We're going to see a little bit later that perfect suppression of second and fourth harmonics is generally not possible, and we're going to look at some math behind that a little bit later that has to do with the duty cycle. It turns out if the duty cycle of the waveform is not exactly 50%, then those even harmonics start to creep in. And then it comes down to, can we always make a limiting circuit, or can we always guarantee that a clock waveform is always 50% duty cycle? There's just some other considerations that come up in there. In the electronics that I passed around, it relies on how well matched those two diodes are, whether or not it produces a nice symmetrical square wave. Any questions? Interesting, or gee, I never thought I'd ask that question because I'd never had an interest in that. I mean, that's what learning about EE is all about. You're going to just find little things lead to other little things. There's these little interconnections between things. Okay, well, this worksheet that I've given out has got one review problem from the last homework problem on last week. Well, we can come back and take a look at that one on Wednesday, but this one, I'm willing to bet that you could do this problem right now in about 2 minutes. Do you want to take a look at it? Just see what you think. If I want to find the average value, A0, remember A0 is just the integral, 1 over T0, integral of T0, x of T, dt. So how many of you think you can only do this by integration? Or can you get away with it some other way?
Find the areas of every piece of one period, and then
Okay.
add
Does that sound reasonable? I mean, integration is finding the area under a curve, right? So if you can find the area under the curve by direct inspection, then you can circumvent having to do the actual integral. So what's the period of this?
6.
Everybody agree? Repeats every 6 seconds. So you know, for starters, T naught is equal to 6. So what I would do is I would just start putting in the areas that make up one period into the top of that fraction bar, and then put it all together. We'll talk about this next time. That's a bat echolocating in the bat cave down at the Shine Mountain Zoo. Slowed down and pitch shifted so that we could hear it. So does somebody want to volunteer the answer? Or what are some of the terms? Okay, so you can answer one part, you're done. Somebody else answer. So he put in an area of 10, that's that first rectangle.
2 is the triangle.
Okay. Okay, what's the next one? Somebody said negative. Okay, so it's -4 times 1 second, so it's -4. Is that it? Is those all the terms? So we got 12 minus 4, and that's 8 over 6, or 4/3. Is that believable? I mean, what we're thinking of, this is the average value, so that says, if I was to draw a line through here, the waveform, half the time it's above the 4/3, so actually, let's see, is that right? 4/3 is about 1, so it's about right in here. So that's where the waveform sits half the time above and half the time below, is when we're looking at it relative to 4/3. Later on in electronics, you'll learn that if you send this signal through a DC blocking circuit, which is a capacitor circuit, that's how it will sit when you look at it on the oscilloscope after it comes out of that DC blocker. So there's other aspects of average value and things that show up in electronics and things. That's it for the day, unless anybody's got a question.
The fundamental frequency, you find it by just doing the 1 over T naught.
Yeah.
So it's 1 over 6 in this case.
Yep. So this is a pretty slow motion waveform. Certainly a slow heartbeat at that.